No, no te sentí.
Estaba escuchando.
Ah.
Okay, so let's start. Okay, very good. So our speaker today is Eder Batista. You know, this as a part of the, at the end of every year we'll have to record the advances that he's done in the PhD. So Eder Batista is going to explain us actually what he's been doing in a visit he did to the maximum institute for themselves organization in the group of party. Okay, so.
Okay, thanks Damian for the introduction, and hello everybody, and thanks for being here this morning. As Damian said, as usual in this period of the year, I'm giving a talk basically. So I'm going to give a talk. I hope that I won't repeat it the two next year. Maybe the last one will be for my defense. So I'm going then to talk about electric network, focus on benefit and limit of control in Braess paradox. As he said, also that is an ongoing work initiated during my research stay at the Maxwell Institute for Dynamic and Self-Organization in the non-linear dynamic group headed by Mark Timmer. So this work is being doing then with the collaboration of Mark Timmer, Benjamin Schaeffer from the MPDI, Eder, Damian, and myself belonging to the IFISC. So the talk is structured as follows. First of all, we are going to give an introduction where we are going to talk about the Braess paradox, give some examples in real life as well, in mechanic and in other fields, scientific field. And we will introduce also the electric network, and then move to the second point where we will present a model of power grid. And the third point will be dedicated to Braess paradox observed or identified in electric network, while the fourth part will be dedicated, where in the fourth part we are going just to see how the secondary control applied to the grid prevents or not Braess paradox, and we will obviously end by the conclusion. Then Braess paradox basically is an explanation of, it's a proposed explanation for a situation where an alteration to road network to improve the traffic flow actually has a reverse effect and impedes traffic through it. It has been discovered by the German mathematician Braess during his research in road traffic network. Braess discovered that adding a new road to a congested traffic network could actually increase the overall journey time. To have a better understanding of that counterintuitive behavior, let's consider that game theory framework applied to traffic network. We have as player 4,000 travelers, and we have to give them a strategy or to find the Nash equilibrium, more or less. Then we assume, first of all, that half of travelers take each direction. One direction, this direction for going from start to A, for example, depends on the number of travelers on the, taking it, okay? Meaning that it can be congested if we have a lot of travelers on the road. So it depends on the number, and the order A to N is fixed at 45 minutes. It will never be congested. This time it's fixed. The same also from the direction going from start to B and B to N. So taking half of traveler in each direction means that the final travel time will be 65 minutes. So 20 plus 45, you have 55 minutes. Then let's assume that the government invests on the construction of a new road, let's say highway, connecting this, the point A and point B, so that the final time in that highway is 0 minutes. Then what will happen? The traveler will have preference to go through that new way. But by doing it, what they just increase their final time. That's what Braess discovered. This counterintuitive phenomenon is then known as Braess paradox. So it has been observed in real life in Stuttgart, New York, and Seoul, just to cite these examples. And it's not so just something particular to traffic network. It appeared also in other systems, in mechanical systems, in electric systems. For example, for the case of mechanical system, you have here a string-spring system. You have two springs mounted in series, and the string connect the support with the end of the second spring, while the other string connect the end of the first spring to the mass. What happens when we cut the spring, the connection here, this one? One could expect the mass to go down, but what is happening actually is that the mass goes up. So someone will say, okay, then the mass lost his weight, but actually since it has a physical explanation, this is a counterintuitive behavior. Okay, what happened here is just that in series, the spring constant is always lower than the spring constant in parallel. It's 1/2 of the spring constant for each spring is 1, then you have 1/2, and then you have 2. Then you spot better the mass. So, as I was saying, in electrical system, it has been also discovered in neural network. In this case, what's happening is you have this network. It's a directed graph. When you add a new link to another direction, the system which was previously synchronized, desynchronized. And the same thing is observed also for the case of stochastically synchronized oscillator. Adding a new link desynchronizes the whole system. It has been also observed in messaging network with this particular toy model, and also in DC electric grid and AC electric network that we are going to show some result. We will just review this work from Dirk and Mark. So let's move then to introduce the electric grid. It's just an interconnected network for delivering electricity from supplier to consumer. As you know, it's composed by 4 components. You have the generators that produce electricity, and that electricity transport through power lines. You have high voltage transmission line and distribution line, and the consumer that use that energy, that electricity. So for a stable operation of the grid, we need to fulfill these 6 requirements. Active and reactive power must be always, or should be always balanced, meaning that the frequency has to be kept constant or fluctuate within this range, that interval. The voltage must be bounded. The total power generated by a generator should be lower than its maximum capacity, and the power flowing through a line should be lower than the capacity of the line. And this last, the power should be produced or supplied with a minimal energy cost and minimal ecological impact. That's why nowadays you can see it is connected in the traditional grid, renewable energy sources. You have solar panel, you have wind power plant, just to try to consume, let's say, clean energy. And that induce in the system some fluctuations, because these renewable energy sources are intermittent. That implies fluctuation also in frequency, together with fluctuation due to the consumer, and that makes the frequency to vary as well as the voltage. So to keep the frequency constant inside every power grid, every power plant, it is affected or it is attached a frequency regulator, frequency or voltage regulator, managed by the governor. Here you have the load frequency control combined to the automatic generation control, which care about the control of the frequency, and the automatic voltage regulator, which manage the voltage. So in this talk, we assume that the voltage is constant. It's not, it doesn't vary. And we are going to model in the next the power grid, the model of the generator, and the frequency regulator. So the generator is a synchronous machine. So by applying the Newton law for solid movement and rotation, you can derive this swing equation, where W is the frequency in the grid, H is the inertia of the machine, of the rotator. PG is the nominal capacity or nominal power of the generator. PM is the prime mover or the mechanical power, the power that makes the turbine in movement. PE is the one that we consume by turning on devices at home. So, as you can see, if we have in the system too much mechanical power, what is happening is that the frequency increases. And in the other way around, if you have more consumption, the power decreases. So to keep it, we apply the governor act 2 times. First, by the primary control, to stop, as you can see, we introduce a perturbation, and the primary act to stop the drop, the frequency drops. And then the secondary control act through this equation to bring back the frequency at 50. That is how the frequency control act in this model. So, and W alpha omega is the frequency sensitive load that takes into account the fact that rotational machine varies as a function of the consumption of the rotating machine depends also on the frequency of the grid. So you have to take into account this parameter. You have to add this parameter to take into account this that fact. And P load is the power consumed by, is the active power consumed, if you want. PS is the spinning reserve, is this power that is added or extracted from the mechanical power to bring the frequency to this target value. So we can rewrite it in terms of deviation from the stable operation. Then we define a new parameter W tilde, omega tilde, as the difference, the deviation of the frequency from the target frequency, as well as the delta PC with the deviation of the mechanical power from its initial stable operation. And that leads to this set of equations. And then by assuming that the secondary control acts faster than the primary, we can reduce this equation to this form. Okay? And you can observe that minus beta I W can be put into this parameter because they have the same contribution, more or less. So we can assume that later we will assume that this alpha plus beta is just considered as a damping. So by now studying the steady state and doing the steady state analysis, we linearize the system around the steady state, and we obtain this set of equations where P, gamma, and A are defined as follows. And P is the matrix will depend on the topology of the network. So, and that lead to this equation, which is obtained by just
Maybe you have not explained the time with sinus, so the coupling.
Yes, sorry. The sinus, sum of sinus theta I minus theta G is the power transmitted to the rest of the network. Sorry. And well, previously I didn't. Maybe here it's a part because this is obtained just for a generator. Okay. So then, if you assume that you have many generators, you have to take into account the contribution, the power that it transmits to the other. Well, now we end up with this equation, and we are going to study. We are making a steady state analysis. We are going to find the eigenvalue or the Lyapunov exponent, and then we will start for the case where we don't have control, meaning that gamma equal to 0. And I wonder you keep in mind that I thought that beta now will be included in alpha. Then you are not going to see any more beta. So in the case that we don't have control, this is the Lyapunov exponent that we have, and the system, the steady state is stable if this real part is negative, or real exponent is negative. And we observe that this is possible just for positive value of the topology parameter mu, or the Hegel value of the Laplacian matrix mu. So to maybe understand, to apply it, let's consider the two-node system.
Yeah, sorry, maybe this mu, you should tell what it is.
Mu is just the Hegel value of this matrix. Matrix of the coupling matrix. That's why I say is the parameter of the basically topology of the network. So modifying mu, you are modifying also the topology of the network. Then modify the topology of the network, you can stay in the unstable region or in the stable region. And for this case, we saw that, and I think maybe or the network, I'm not sure, the network is stable if this parameter is positive. Well, we apply it now in the two-node system, meaning that we have the generator and you have a big machine or in an industry. And theta 1 is defined as the phase of the synchronous machine in the generator, and theta 2, the phase of the machine in that industry, for example. We focus on the difference of phase, and we can write down why. Because you remember I talked about this fifth requirement. The power flowing through a line should be lower than the capacity of the line. And that is defined, that is basically the power that this generator sent to this machine or vice versa. Then to make it be possible, you have to play with the difference of phases that we define as phi. So we can write down the equation by taking the difference. We have this set of equations, and this set of equations has two steady state. The first one obtained, of course, by equaling this, by putting this equal to 0, you end up with this steady state, and we can see that steady state exists if and only if the ratio is lower than 1. And that means basically that the power, as we were saying, has to be lower than the capacity of the load to obtain this steady state. So that steady state is always stable because, as you can see, it can be either real with negative Hegel value or imaginary with negative real part. But the second fixed point, steady state, which is given by S2, is always unstable because it has a negative, its Hegel value is either negative, has real negative part, or positive real part. So when delta P is equal to 2K, the two steady state collide, and you obtain a snake, which basically means that the system goes to a state where it's oscillating indefinitely. Then that particular state describes the power outage in our network. So when we have a power outage, that means basically that the system is not anymore synchronized. The system is oscillating in non-synchronous. I mean, if you go up if delta P is greater than 2K, of course there is nothing. There is no steady state. But when it's equal, you have this situation. So this phase diagram shows us also all the dynamic or all the state where the system can be found. By taking the average, by taking equal to 0, the derivative of the average over a period of time of the energy of these two node system, we are able to extract this term, which help us to find the border between the region of coexistence of solution, meaning that coexistence of limit cycle, because in that region You have a limit cycle and you have also a steady state. But you have to see that in this region, the power, this delta P is lower than 2K. That means it can happen in the nature because that depends also on some initial condition. It can happen that when you turn on, when the grid is on, for example, it's facing directly an outage. That is because it was in this kind of situation, and that happened when the damping is too small. You have this state which exists. And in the other region, you have the system is globally stable. And in the inside, you can see the time series of the phase difference. Now, let's go into the work did by Dirk and Mark. They built a toy network. It's an Ethernet network where in red you have the producer or generator, and green you have the consumer with power here, or the generator's power P and the other minus P. You have three configurations. First is the original configuration. The system here you have theta I tilt, and here you.
So what is that's the phase?
Yeah, it's the phase. No, it's the phase of every node. I don't know why I turn it like that. Well, theta I divided by P, and you see for the original network, the system is synchronized, more or less, because the phase are constant. And okay, when we add, we upgrade the capacity of the line, what's happening is that the system loses the synchrony. And
just one remark. In this system, in the original system, in confusion, just when the system is synchronized, the frequency is the same, but the phase can never be the same, because if the phase were the same, there will be no transmission of electricity on the grid.
Exactly.
So the fact that you have different phases is what you expect. You expect different phases, but the difference should remain constant.
Exactly.
The phase difference is proportional to the capacity of each of the lines.
And here, all the line has the same capacity.
Yeah.
Nice. Thank you. So, as Damien said, to ensure the synchronization, the overall synchronization, we have to, in principle, I should tell it before, the system can be frequency synchronized, meaning that they are oscillating with the same frequency, and then the difference is 0, and you have the phase synchronization. In principle, the perfect case will be that they oscillate with the same phase, but that case means that there is not energy transmitted to each other, and they are synchronized when here the difference of phases is kept just constant. So what is happening when we upgrade the capacity of the line? Actually, the system loses its synchrony, or the steady state is lost, and we are going to explain it later. And the same observation is made when a new line is added. Upgrading a line, in principle, should help to improve the stability of the supply network. Because as I present for the two node, you saw that if delta P is greater, delta P has to be lower than 2K. Then someone could expect that if I put more capacity on the line, in principle, my system should remain stable. But that is not what is happening. That's why, and the same thing also, when you add a new line, you should redistribute the power to support. I mean, here we can expect that this line is overloaded. If you add a new line, the electricity will flow through it and we reduce the power in the other line. So what we observe is basically the opposite. I mean, the system desynchronized, and that is why we say that we identified in this system Braess paradox.
It's important that in the two cases you connect two generators and not a generator and a consumer? Or is the same desynchronization occurs when you connect two consumers or two?
We are going to see it later with another case. Yes, but we didn't. Yes, of course, the same thing happen if you connect two consumer. You mean, or just one generator and one consumer? That was what. One consumer and one generator. To be honest, I didn't try it, but I tried for the case where you connect the two generator, two consumer. You have the same behavior.
I understand you will not always get this effect.
Mm-hmm.
Sometimes some things which are good, but some that they naively seem to work and they don't.
Can you further simplify the network and still have the same result, or this is the minimum complexity?
That is the network in which we found this behavior has been found. If in other, yes, for bigger network, in the paper of Mark, they showed that it happened also.
For smaller, no.
Well, you should have a cycle, cyclic network, as we are going to see, that this effect is not due to the topology of the network, and that occurs when you have like a closed network adding. I will go in later because it's the explanation is the explanation that we are going to give now, because this doesn't, the fact that you add a new capacity, you upgrade the capacity of the line, or you add a new line, doesn't change this requirement. It's always very fulfilled, because that is the requirement to obtain a steady state in the system. So why don't we have then a steady state? Because actually, by doing it, you are modifying the geometry of the network, and there is a constraint, a geometric constraint, which is not anymore fulfilled. In principle, if you have a closed path, a cycle, the phase difference, the sum of the phase difference should be always equal to 0. So one they saw is that actually by doing, for example, for the case of adding a new line, by doing it, this quantity is not verified, and that induces then the instability in the system. That's why they say that the steady state doesn't.
Can it be 0? Can it be 2 pi instead of 0?
Yes, 2 pi. Yes, it can be 2 pi.
I mean,
It's 0 modulo 2 pi.
yeah, but then you can have several non-equivalent states. It's a stable.
So no steady state exists because of that geometry frustration. And also another idea why that could happen was that maybe in this graph you have you have the parameter, the other parameter. In this plot, this has been plotted by considering that if there is any steady state in the system, this order is equal to 0. And what it observed here is that for the original network, you see that the critical capacity, when you pass the critical capacity, when K is greater than the critical capacity, we start to have steady state in the system. By upgrading a line, by increasing capacity of the line, we increase the critical capacity of the network, meaning that the capacity that you used in the previous in the original network now is smaller than the new critical capacity, and that doesn't allow the existence of any steady state. So then adding a capacity actually should reduce the synchronability of the network. Now let's move to the case where we add the control in the system, and we start also from the same set of equations that we had. We define the Hagen, the Lyapunov exponent, and we plot the real part of the Hagen-Lyapunov as a function of the control parameter gamma. In what?
So you put this or it's just a linear?
Yes, linearization of the previous system. And just by considering that gamma now is different from 0. And gamma is the control parameter for each generator or each node. So by increasing gamma, what we observe is that the critical, the region, the stable region is increasing. So gamma actually acts to improve, we can say, or to enhance the region of stability of the network. So we continue by taking now the two-node system, and we write down the corresponding equation, taking looking for now the steady state. And the steady state exists if you fulfill this, if these two equations are equal to 0. Okay? Remember that I told you that we want phi to be always bounded, compressed between minus pi over 2 and pi over 2, to be sure that it should be open here, to be sure that the power will never be greater than the capacity of the line. By applying this, we use the intermediate theorem to value to be sure that this equation, which is transcendental, you cannot find analytical result, but by doing it, we are sure, we try to prove that it contains at least one solution in that interval. And that allows us to have the condition for existence of a steady state. And clearly, by taking gamma equal to 0, the case that we don't have any control, we recover the previous condition. So, and also, from that, we can see that the critical coupling is modified. Now the critical coupling is the previous critical coupling without a control minus a parameter function of the control parameter gamma. And that will help us to understand what is going on now when we consider the previous network, Eder network. We compute here the original network, and we observe in the first row you have the uncontrolled case, and the second the control case. What you observe is that for the original network, of course, nothing changed, it's synchronized. When you increase the capacity, you upgrade the capacity of the line, when it was desynchronized here, it's still synchronized. And also when you add a new line, the steady state still exists. So using, what we can say is that using the control in our system, what it's doing is just to, that it ensures us to always have, many times, yes, but not maybe always, but that ensures us to have many times, to have a steady state, and to have a synchronized network. So now we plot, we have here the network with the power flowing through each line. This is the original case. As what we were talking, here there is no power transmitted. You can guess why, as well as here, because the two nodes, they have the same phases. And here the power transmitted is 1, meaning that the difference of phase is pi over 2. This is for the case, and for this case, the system was stable. Because K here is 1.03, we are close to the critical capacity, which is 1, actually. And for the case with control, what is observed is that the control helps to redistribute the power flowing, and it reduces. We go from 1 to 0.92 and 0 to 0.02. And there is another thing important, is the inside every node you have here the mechanical power of the generator. And because we say that the load is kept constant, you remember, the load is kept constant, then we just plot here inside the mechanical power, and we see we cannot really appreciate, but it changed for the case of the controller, because it's modifying the mechanical power to bring the frequency to 50. Then the mechanical power, in the case without control and the case with control, are different. By adding a new link, a new line in the system, you see for the case where here there is not steady state. So we just stop the simulation. As you observed previously, I present that the system was desynchronized because there is not anymore the state there were not any more steady state in the system. But then we stop just the simulation and we observe that even by stopping, there are lines which are overloaded. This line, for example, these two also are overloaded. When you add the controller, it reduces the power flowing through the line by keeping the network stable. So that is one of the results that shows us that using the control in the system help the system to keep its synchronization. Now we take the more or less real case, not real case, but real situation, because in the previous case we controlled all the nodes, and they are generator and consumer. Now we assume we control just the generator, which is a probable situation, and the consumer are not controlled. What we observe by upgrading the line 3, 4 is that line overloaded and the system desynchronized, meaning that even with the control in the system, upgrading, improving the network lead to a counterintuitive behavior, which is the desynchronization of the network, which means that even in presence of control, Braess paradox exists in this system. And that brings us in the conclusion. So we presented the model of secondary control. We compute the steady state analysis of the power grid as function of the network topology and the control action. We demonstrate that the secondary control prevents the synchronization in network when all the nodes are controlled, and in the case where the nodes are not controlled, we can still observe the Braess paradox in our system. So I would like, by ending this talk, to thank all the contributors to this network, to this of this work, and thanks for your kind attention.
Thank you very much. Is there any other question? You have said that the behavior of the consumer is crucial to stop the paradox, but you have shown an example. So is this general? You always need control from the consumer side. Is that general?
For this case of for this network use, yes, we need to control the consumer to ensure the global stability for this case, and also for other cases. That's why during the tweet last year, we conceived a demand side example, dynamic demand control, with aim to stabilize the frequency to go to encourage consumer to participate by turning off or turning on their device according to the frequency of the grid. This type of participation, yes, is crucial to ensure the stability of the network. I think so.
What you mean is that it helps. It means that it's not crucial. You can have cases where so the point that if you are controlling the demand side, of course, will improve the stability overall. That's what it is. It doesn't mean it is crucial in the sense that you can also avoid Braess paradox. Maybe in some cases, yes, only with controlling the machine.
That's what I say for this case of story model, yes.
If you have control in the demand side that you can work.
No. For all network, no.
Let's ask a simple question. So you can join together 5 and 8, and the system still believes in this, no?
I can join together.
5 and 8. And the system is basically
5
you
and
can
8.
still simplify that bit.
By joining 5 and 8, well, the symmetry, I don't think they are going to. I mean, you can join whatever, yeah, but yeah, if to see how the system will behave later, maybe we can try it. I don't know.
And it just, since you're creating a toy example, the less complex is the risk, the better. And the question would be, can you even join 27 or not?
Well,
Yeah, 2 and 7.
he is different.
Yeah,
So you
perhaps you have the same phenomenon.
Maybe.
Maybe. I mean, to have a.
You can join 5 and 8 assuming that you double the size of 5 and 8. If not, you change the topology because these nodes are supposed to be all of the same size.
Ah, okay.
If you join 5 and 8, then it could be 1, but
So
with
you
a
need
double
the
wall.
double, you need double wall.
Well, of not, you have to try, I don't know, because it depends on the topology of the connection. This is the example they choose, and this is why they started with this because this is the one that Martania they use in the original paper. So, but yeah, always there are simple schemes in which.
Okay, so thank you very much.
So not you don't get the same balance.
So basically,
But you probably
yeah,
always